So we will continue to work on the energy. So here I will talk about the energy of a energy due to acceleration of the particle. So in other words, m into a. And then let's assume that the particle moves this path, and then this is the path that particle moves, shown with the S. And then we said that the force, the work or energy will be the m into the ds. Okay, we will take a small distance and then the acceleration. So let me add one more thing here before I move. We have the work, and then we have the energy. Okay, so you have to understand the difference between these two. The energy is so it is defined at a point. So what does it mean? It is defined at a point. It means that for a given particle, for a given time, you can find the energy at a point, or let's say time. This may clear the point. And the work is a process. Okay, so if I give you the time and ask you the work, what's the work at this time? It doesn't make sense. The work is a process, so I should tell you from this time to that time. Or even I don't tell you, you have to understand that it includes the time. For some time it needs to happen. But for energy, it's not like that. If I give you the time, you can tell me the energy of the particle. Okay, that's the main difference. Or you can say the work is energy in transit. Okay. So like it transfers energy from one place to another one. That's the work. But the energy is the capacity to do work. Let me add this one. Okay, so this is the main difference. So to find the energy due to motion of the particle, I will use this one. The next is that so the particle will have the normal acceleration and then tangential acceleration. Let me show it as well. So it will have the an, and then it will have the at. But the an, it doesn't contribute to the acceleration magnitude. It only contributes to the it doesn't, let's do this way, it doesn't contribute to energy. Why is that? Because if you take the m an into ds, so this dot product will be 0. That is because the angle is 90 degrees. So you can notice the particle moves this way and the an is that way, so that's 90 degrees. And then one more thing, let me show you the s as well so you can see. That is ds. As you can notice that ds and then at are in the same direction. So I will show this one as mat into ds. Okay, and they are in the same direction. So theta is 0. So therefore I can show it as mat into ds. Okay. So let's find the energy now. So energy will be that. Okay, one more thing, but they use the same formula of F into distance, or F into dr. Okay, then the energy will be if I go back, MATDS. Okay, and then let me put 1 to 2 here. So I know that AT is dV by dt. Okay, but even this one doesn't solve the problem. So because we have to integrate it, so what you can do is that you can put that this one as 1 to 2, so that M and the dV and then ds by dt. And then I know that this is also velocity, so that will be 1 to 2 mv and then dv. And that is the simple integration, that's mv2 squared minus mv1 squared by 2. And then you know from physics, this is kinetic energy. Okay, so what it means is that the acceleration of the particle, the energy due to acceleration of the particle is the kinetic energy. Okay, so if you then the Newton's second law, we had said that the net force will be equal to the mass into the acceleration, and then now we will say that the work and then energy principle, the work net is the kinetic energy 2 minus the kinetic energy 1. Okay, or you can say that the change in kinetic energy. That is the main part of the derivation. Okay, so in the next recordings I will solve problems on this one, but first let's identify the work due to weight. So say that we have a particle and then it has a mass of mg. Okay, and then let's select the coordinate here. So this is the coordinate y. Okay, so if I write the dot product, then I know that I should write the F into the dr. Okay, and then dr has 3 components, because then let me show you. If it is the particle here, and then if I show the dr, this dr will have the one is that it will have dz component, then it will have dy component, then it will have dx component. So we call it x. So we can call it x, and we can call it y, and then we can call it z. And then in that case it will be dy, and it will be dx, and that will be dz. Okay, and then you can say that dr is equal to dxi plus dyj plus dzk. Okay, so this is dr, and then the force is the mg. Okay, if you take the dot product of this one with that one, you can see that, sorry, the dr, you can see that mg, that one is in the y direction, so I can call it as mgj, and it is positive. You can see it is in y direction, that's positive. Dr if you take the dot product between these two, you will get an mg dy. Okay, you can see, so the work done by weight is positive. If force and then motion are in the same direction. Okay, and then the work by the gravity, that will be equal to mg dy. Or you can integrate it, work due to gravity, it will be that 1 to 2 mg dy. That will be mg y1, sorry, y2 minus y1. That will be mg into delta y. So otherwise, if it is in the opposite direction, then you will have that weight due to gravity, it will be negative mg delta y. So you have to be careful here, yes? Just identify the force and then the direction of the motion. Similarly, work done by spring force, I will not show the derivation, that will be that work by spring, that will be negative 1/2 ks1 squared minus ks2 squared. So no, sorry, let me just correct it. ks2 squared minus ks1 squared. That is the work done by this spring force. So for this one, I will not show the derivation, but I will need to show that what is the spring force. So if I have a spring here, and there is a particle attached to it, and it moves in that direction with, that's the position, and then I can call this one as, that is unstretched position. So in this case, for example, so that is external agent, the body, let's say external body pulls the spring. Okay, and therefore work done will be equal to the F into the S. That's what we mean here. But F into ds, sorry, F into ds. And then we know that the force of spring will be equal to negative force by external body. Okay, by Newton's third law. Okay, then in that case, it will be that the work done by spring force will be negative, then we will have the F into ds. Okay, that's very important, that spring force is opposing. That's the reason we have a negative sign here. Okay, because we take the force of the spring, not the force of the external agent. The particle itself cannot move in that direction. Some external agent force acting on the particle, and it forces to move in that direction. But since we are considered in the spring force, we take the negative direction by Newton's third law. And why we are interested in spring force? Because, so I'm at this one as well. Because we know the spring properties. What are they? It is the K, stiffness. And then we know the stiffness of the spring, which is K, and that's the reason that we are dealing with the the spring force instead of the external agent. Okay, with this in here I will stop the recording and then I will move on to problem solution.